Alright, so in this video we're going to continue studying nilpotent groups, but one thing they like to mention leading to the nilpotent groups is something that's useful for other purposes called Frattini's argument. And so one version of Frattini's argument is the following. G is a finite group. H is a normal subgroup of G. And P is a CELO subgroup of H. Then G is actually equal to H times the normalizer in G of B. And the index of G, H and G, divides the size of this normalizer. So this thing has proven useful enough in group theory to actually have its own statement. It's kind of weird to call it an argument instead of a lemma, but history has caused this to happen. And there's not just one Frattini's argument, there's another slightly more general one that we're going to use as well. And to distinguish it, I'm going to call it the generalized Frattini's argument. This is called looking ahead to later. There's a particular theorem we want to prove called the Schur-Zasenhaus theorem, and we're not going to follow the proof in the textbook because it's in a chapter we're skipping, and so the proof we are going to do uses a generalized Frattini's argument, so I have to give it. So the generalized Frattini's argument goes back to group actions instead. So you have G acting on a set X, and H is a normal subgroup of G with the following properties. 1. H acts on X transitively. In case you need the reminder, that means for all X and Y in X, there's an element in H such that H dot X equals Y. Note here, whenever you have a subgroup of a group, and G acts, the larger group acts on a set, then the subgroup also acts on the set the same way. The second property is that if you look at the stabilizer subgroups with respect to this subgroup, it's always trivial. These two properties together are usually coupled by saying the action is regular. So if I state that term, I mean these two properties, but here I decided to just state the conditions together. So suppose you have this case. Then G is isomorphic to H semi-direct product with the stabilizer in G of any point. So here's the outline of the video. First, I'm going to prove the generalized Frattini's argument, then show how you can use it to prove the original Frattini's argument, and then apply the original Frattini's argument to nilpotent groups to get another equivalent definition of nilpotent groups. Worth noting, of course, that this is saying that you can write H is equal to Gx. There's also the weaker condition, where if you only allow one, then all you get is that G is equal to HGX. It's the second condition that gets you the direct product, by which I mean semi-direct product. So let's look at the proof. So first, I've got G acting on a set X. I've got a subgroup of G that's normal, and hx on x transitively. Well, let G be any element in the group, x and be an x, and let y be equal to gx. And for a moment, let's assume that it's not equal to x. Then since y is transitive, or hx transitively on x, you know that y is equal to h times x for some element in the subgroup. So you got h times x is equal to g times x. In some sense, the point is every action by G is duplicated by an action by H. And what does this imply? It implies that G inverse H, x is equal to x, which means that G inverse H is in the stabilizer. Of x. So G inverse H is equal to some sort of element in the stabilizer, let's call it k. So doing some arithmetic, h is equal to gk, g is equal to hk inverse. So congratulations, g is in this set, hgx. So taking an arbitrary element in G, we managed to write it in this set. Notice since I'm assuming H is normal in G, this set is in fact a subgroup of G. So we get that part for free. So every element in your subgroup is in this subgroup. And so G must be equal to this subgroup. What happens in that weird case when g dot x is equal to x already? Well, then G is already in the stabilizer to begin with. So then you could just write G is the identity times G, and we're fine. So we're good to go on that part of the Frattini argument. Of course, now it's worth pointing out we have H gx and all of G, and we have normality here. There's this diamond isomorphism theorem that says we also have normality here. And moreover, that the index of H and G is actually equal to the index of this intersection, which of course, since this intersection is a divisor of the stabilizer, this actually tells you something more that I didn't state in my version of the Frattini argument, but we will need for the other part, which is not only do we have this fact, but we also have that the index of H and G divides the size of the stabilizer. So to complete my version, the generalized Frattini argument, for later uses, we need to see what happens when H acts regularly on X. Because I actually want semi-direct product and not just this product operation. What I want to note is we want H intersect the stabilizer to be the trivial subgroup, because then our theorem on semi-direct products tells us that HGX is isomorphic to this semi-direct product. And there's lots of theorems where this is useful. Well, what would it mean for H to be in this intersection? Well, it means that it's in the stabilizer. So H dot x equals x, but we already defined property 2 that the stabilizer subgroups are trivial for every element. So, in fact, that tells you that this intersection must be trivial. And so that's all you need. Since it's trivial in that case, then you're done. It must be the case that this intersection is trivial and you actually have a semi-direct product. And so we'll keep that in our cap for later. Much, much later, but later still. Now we can get back to the original Frattini argument. The original Frattini argument proceeds by just actually taking a particular group action. Namely, you take a group G and a subgroup H, and you let X be the set of CeLO P subgroups of H. And you let G act on this set in the natural way by conjugation. Naturally, this conjugate is a subgroup of this conjugate of H, but because H is normal in G, that's actually equal to H. So even though I'm acting by elements of the larger group, this conjugate is still a subgroup of the smaller group. And so I actually am still staying inside of X. That is worth pointing out, because if I take a bunch of subgroups, if I let X be a bunch of subgroups of H and I act by a larger group by conjugation, there isn't a guarantee that conjugating subgroups of H by elements in G gives another subgroup in H. That's only true because of normality. Naturally, the action isn't always regular, but it is transitive when you restrict to H. If that's true, then we'd actually have what we need to apply the generalized Frattini argument and say that G is equal to H times the normalizer with respect to this action. Oh, but what is the normalizer with respect to this action? It is the normalizer, not the normalizer, stabilizer. It is the normalizer in G of P. And then my comment about index for in general immediately applies the condition we wanted here as well. So I only need to check this claim. And so how do I check this claim? Well, let P and Q be two CeLO P subgroups in H. Then by CeLO's theorem, Q is equal to HP, H inverse for some H in H. So CeLO's theorem already tells you that this action is transitive. And so that's all we actually needed. So we have a transitive action, therefore we actually have this argument. You can also check the proof of the Frattini argument in the textbook, and you'll see some of the details are actually the same as what I had for the general case, just restricted to the particular group action they were interested in. Now let's apply the Frattini argument to another characterization of nilpotent groups. So a finite group is nilpotent if and only if every maximal subgroup is normal. So again, it's another equivalence. Technically, we could have included it in the list of 4 from the previous video. The obvious reason why they don't is because it turns out the easier way to prove this is 1 implies 2 and 2 implies 1. And so including it with the other proof makes it even harder to follow. Not to mention we had to prove a lemma in order to do this. We actually noticed that we already proved this result in the case of p groups. A p group, every maximal subgroup is normal, but we actually stated more information there. It's also of index p. In general, we can only just say they're normal. So let's do the proof. For direction, we're assuming your group is nilpotent, and we're going to let M be a maximal subgroup. You're going to notice in this proof that we're going to use a lot of the different equivalencies. So since it's maximum, it is in fact proper. So by one of the equivalent definitions of nilpotent subgroup, it must be a proper subgroup of its normalizer. But of course, it's a maximal subgroup. So this normalizer has to be all of G. Also, every group is normal in its normalizer. So it's normal in G, which is exactly what we wanted to show. This part was just like the case of p groups. I assume that this result for p groups. So now we're going to assume the reverse. This is the part that uses Frattini's argument. We're going to assume every maximal subgroup is normal. What we will actually try to show is that every CeLO P subgroup is normal. If we can do that, then we're done by that statement about the following are equivalent. So let P, capital P, be a CeLO P subgroup. This is going to be a proof by contradiction. We're going to suppose P is not normal in G. Then this implies that the normalizer is not all of G, so it must be a proper subgroup. In particular, that means it must be a subgroup of some maximal subgroup. Because that's something you can do. If it's not by definition of maximality and the fact that you're working with a finite subgroup, if it's not all of G, then here I should actually include this in case it is actually the maximal subgroup itself, but the point is, by possibly making it larger, it's contained in a maximal subgroup. In order to use this condition, you have to be assuming it's not all of G. So it's important that you actually have to do this proof by contradiction. I can't find a way to avoid it. So then Frattini's argument, and here's where I'm using M as normal because maximal subgroups are always normal. Frattini's argument tells you that G is equal to m times the normalizer in G of p. Of course, since the normalizer in G of p is actually already a subgroup of M, we have that G is equal to M, which is a contradiction because maximal subgroups can't be equal to the group that they're maximal subgroup of. So either somewhere there's a theorem that had a false proof, or our assumption is wrong. Clearly our assumption is wrong. So it must be the case that P is normal in G. And yes, I did in fact spend at least some time trying to think that there's a way to wheedle our way around it to make it a direct proof instead. But the key item for this contradiction argument relies on using maximality, a maximal subgroup containing your normalizer. And the only way to get a maximal subgroup containing your normalizer is to assume that the normalizer is not all of G. And so you have to do contradiction in this case. And this actually shows one reason why contradiction arguments can be very useful, because they allow you to make assumptions that allow you to apply theorems that you otherwise wouldn't be able to apply in order to contradict other definitions. On that level, this is a higher level contradiction argument because the contradiction you're making is that you assumed you had a maximal subgroup and you managed to prove that it was actually equal to all of G, which is not supposed to be possible. You start to find these types of contradiction arguments in higher mathematics where you end up contradicting some other theorem rather than just the statement you just made.